Yeah, hello everyone. Am I audible?
Yes,
Yes,
yes.
sir.
Okay. So we'll be discussing the week 5 assignments today. Okay. We will start with the question number 1. It says that if let V and W be Banach spaces, T is a continuous linear operator from V to W. Which of the following statements are true? Yeah, just a minute. Yeah. Okay, so the statements are first one is says if T is invertible if and only if T star is invertible. Okay. So here the invertibility means that bijective, the operator is bijective as well as inverse is also continuous. Okay, that's what we mean by saying invertible. But since we have given both V and W are Banach spaces, it is enough to show that the operators are bijective because by bounded inverse theorem, it guarantees that the inverse is also continuous. Okay, so we'll try to prove. So the first statement. So the statement is T invertible if and only T star is invertible. Okay, let's start with T being invertible. So we want to show that T star is invertible. So at first, what is T star? So here we just have Banach spaces. Okay, so T star here is kind of transpose operator which is from Y star to X star. So dual of Y to dual of X. But if we had a Hilbert space, suppose it's the same as disjoint operator. It can be identified. Suppose T be invertible, then now we have T star from Y star to X star. How is it defined? T star of any functional G, okay, is now a functional on X star, I mean functional on X, so it's given by T star G at X is equals to G of Tx for all X belongs to capital X and G belongs to Y star. Okay, this is how it's defined. Okay, this is T star. We want to show that T star is also invertible, and it's enough to show that T star is what do you say bijective. Okay, so let some G belongs to null space of T star. Okay, we want to show that G is identical zero functional. Then null space of T star will be singleton zero and C star will be 1 1. So what does this mean? This means T star of G, T star of G is now in X star, right? And T star of G is identically 0. So that means G is in null space of T star. But T star G is identically 0 means T star G of X is equals to 0 for all X belongs to capital X. That is G of Tx equals to 0 for all X belongs to capital X. Okay. Now G is in Y star, right? Null space of T star is contained in Y star. Okay. So a linear functional, if it is 0 on every domain point, then we say that G is identical 0. This is the consequence of Hahn-Banach theorem. Okay. So claim is G at Y equals to 0 for all Y belongs to capital Y. If this happens, then G is identical 0. Okay. We'll try to prove this thing. This is very easy. You take any Y, capital Y. Since T is invertible, T is onto. T is onto implies there exists an X belongs to capital X such that Tx is y. Okay. Now Tx is y implies what? G of Tx equals to G of y. But what we know here, G of Tx is 0 for all x belongs to capital X. This implies G of y is also 0. This is happening for all y, which guarantees that G is identical 0 by a consequence of Almanach actually. Okay. That means null space of T star is singleton 0 and T star is 1 1. Now only thing we have to show is T star. So this will imply that T star is 1 1. Now the remaining claim is T star is onto. We have to show that T star is onto. T star is onto means what? T star is from Y star to X star, right? That means for every linear functional f, that is what we have to show is for every linear functional f belongs to X star, we want to find a G belongs to Y star such that T star of G is equals to f, right? This is what we want. G belongs to Y star. Okay. So what we do is we have given an f belongs to X star, and T now from X to Y is an injective is a bijective operator we know. Actually, it's an invertible operator. That means T inverse from Y to X is continuous. Okay. So now I'll consider this G as F composite T inverse. This will be from yeah, okay, where will this be from? Y to R, right? Yeah. This will be from Y to R. That means it's a linear functional on Y. But since T inverse is continuous and F is continuous because F is a continuous linear functional on X, this implies G belongs to Y star. Yeah, that's what we wanted. G belongs to Y star. Now what is T star at G? It is G composed with T. But what is G? G is F composed with T inverse composed with T. And you know T inverse composed with T is identity. So T star G is F. That is what we wanted. Okay. So for every F we got a G. Okay. That means T star, yeah, T star is invertible. Okay. So, yeah. This goes to the first option. So yeah, now we go with the second option which says T and T star are injective and T has closed range and T and T star are both invertible. Okay. So second option which says T and T star are both injective and range of T is closed, then T and T star are invertible. Okay. So what we know is T and T star are both injective. Okay, that's all we know. If we prove that T is invertible, then by 1 it follows that T star is also invertible, and we are at 3. Okay, so also for proving the invertibility of T, it is enough to show that T is onto. Okay, because X and Y are given Banach spaces, sorry, V and W. So any bijective continuous map is invertible. Okay, that means its inverse is also continuous. Okay, so consider R to be range of T. Okay, claim is whole W. Like T is an operator from V to W right now we have, and V and W are Banach space. Okay, so consider annihilators and all. We have seen the annihilators thing in the last session, or also in the last videos sir have talked about the annihilators. So R is a subset of Y. Okay, so what is R perp? This is set of all linear functionals on Y such that G of I call it, suppose small r is 0.
Equal to 0.
Yeah, for all r belongs to capital I. What that means? G of Y star such that G of capital R is what? Range of T, right? So for every element in the range, there exists a pre-image, right, in domain. That means I can write this as T of X for all X belongs to capital X, right? I mean, range space looks like this only. So, but this is what? G belongs to Y star such that G composed it, or simply T star G is identical 0. This is null space of T star, correct? But we know that T star is also injective, right? We know T and T star both are injective. That means T star, null space of T star is singleton 0. That means R perp is singleton 0. And what we know is range R closure is equals to R perp perp. Okay. But here, because R perp is singleton 0, what is R perp perp? Okay. R perp is a subset of Y star, right? Yeah. So its perp will be whole space Y. That means R closure is whole space Y. R means what here? Range space of T is the whole space Y. But there is another condition also on T that says that range space of T is closed, right? Range space of T is closed means what? Range space of T closure is same as range space of T. What we got is T is onto. So T is 1 1 onto continuous. Hence, by bounded inverse theorem, T is invertible. And also, by one part of this thing, T star is also invertible. Yeah, this follows. Third says that T is injective. If T is injective, then T star is surjective. Okay, this is wrong. Okay, I'll write here. If you consider T an operator from L2 to L2, suppose, given by, now the mapping I'll give, x1, x2 and all, this is a sequence which goes to the sequence x1, comma, x2 by 2, x3 by 3, so on. Okay. this map T. You try to prove that T is injective but not surjective. And in this case, T star can be identified with T. Okay. Like here, L2 is in basically Hilbert space. So for Hilbert space, it kind of relates with adjoint. Okay. And T star, which is an adjoint of T, is same as T here in this case. Okay. You try to prove this thing. Okay. It's very easy. T is injective is very easy. Surjective, you have to find an element which doesn't have a pre-image. Okay. In L2. The pre-image should be in L2. That is square summable sequences. So this is wrong. Just a minute. Yeah. Question number 2. V and W Banach spaces. A is a closed and densely defined operator from the domain of A, which is subset of V to W. So, sir also explained some properties of this kind of operators in the lecture videos, which was null space of A uh, was same as range A star perp, and null space of A star is same as range A perp. Then null space of A perp contains range A star closure. Fourth one says null space of A star perp is equals to range A closure. Okay, so we'll try to see what was very clear with these properties and these options. Is the screen properly visible to you, right? Anyone? Hello?
Yes, sir.
Is screen properly visible, right?
Yes, sir.
Okay, okay, thank you. Okay, so first option says if A has dense range, then A star is injective. Okay, what do you mean by A has dense range? It means range of A closure is the whole space W.
Yes, sir.
Okay, yeah, yeah, okay. So what do we have? We'll use the fourth option here. What do you know? The range of A closure is whole space W, which implies null space of A star perp is whole space. That means null space of A star. Okay, yeah, null space of A star closure will be contained in. See, what do you know is null space of A star closure will be contained in null space of A star perp, right? But this is singleton zero only, and this contains singleton zero. So no issues. And null space of A star is a closed set, so null space of A star will be singleton zero. That proves that A star is injective. Okay, just simple manipulations of closeness. Then second option B, if A star is injective, then A has dense range. Okay, so A star is injective, so that means null space of A star is singleton zero. So we want to show that range space of A star, range of A closure is the whole space W. So null space of A star is same as range of A perp, right? From the second property. This will imply range of A perp will be whole space W, and this is same as range A closure, right? So range of A closure is the whole space W. That means A has the dense range. Okay, this is correct. For the third option, it says that if A is injective, then A star has dense range. Right? But uh, but what we have here is the third property. Range of A star closure is contained in null space of A perp. Okay, so null space of A perp in this example, if A is injective, then what we know is null space of A is singleton zero. This implies null space of A perp is whole space X, right? But oh wait, null space of A perp is whole space X star. Hmm. But range of A star closure is contained in X star. Okay, so we cannot guarantee that we don't have enough, sufficient information to say that range space of A star closure is equal to A star. Okay, this can be a strict inequality. Sorry, strict containment. So we can't be sure that range is dense. Range of A star is dense. Okay, the third option need not be true. Okay, I hope this is clear. Then we go to question number third. V be a Banach space, W a subspace. Which of the following statements are true? If W is closed, then the weak topology on W is the topology induced on W by the weak topology on V. Okay. See, this is sir has explained the exact same statement in the class. So there is one lecture videos. Weak topology one, I guess. Yeah. And that sir has explained this thing. You can watch the video. It's exact same. Then part B I will show. If W is closed, then it is weakly closed in V. Okay. So in fact, W closed means what? This is norm closed, right? So there is one bigger result. Result is XB nonlinear space and W be closed convex subset of X, then W is weakly closed. Okay. So we have this statement X be a nonlinear space, W be a closed convex subset of X, then W is weakly closed. Okay. So if this from this statement, it straight away follows that W closed in V, then W is weakly closed because W is a subspace. Every subspace is weakly closed. Okay. So I'll just prove this theorem, this lemma. Okay. So W is norm closed and convex subset of X. So by Harmonic separation theorem, see what we want to show is W is weakly closed, right? or equivalently, complement is open, is weakly open. Correct. So what I'll do is I'll take a point in W complement and I'll try to. Hello, is my voice clear? It's not?
Yes, sir. Your voice is clear, sir.
No, Anjani Vishwakarma is saying my voice is not clear. Maybe your internet connection is unstable, or you try to rejoin maybe.
Yes, sir. Now it is clear.
Okay, okay. Maybe there is some problem can be there. My actually health is not good, so maybe audio had some problem, but try to manage this for today. Let X naught belongs to W complement. So I want to find a weakly open set. Okay, like what we want to do is we want to find a weakly open set. I call it suppose O, such that X naught contained in O will contained in W complement, right? If I can find this, then this will imply that W complement is open, correct? This will imply. So we want to find a weakly open set O containing X naught. So what we have, W is a norm closed set, closed convex subset of X, right? So and consider X naught a point which is not in W, right? It's in W complement, which implies by Hahn-Banach separation theorem, there exists a functional such that f of x is strictly less than alpha, suppose is strictly less than f at x naught for all x belongs to W. Correct? This is just Hahn-Banach separation theorem. So yeah, this happens. F is now continuous linear functional. Okay. So by Hahn-Banach separation theorem, we got a continuous linear functional f such that it separates W at the point x naught. Okay. But what does that mean? If I consider now O to be f inverse of this set alpha to infinity, right? See, f inverse of alpha to infinity. This this O is weakly open, right? Because this is how we define the weak topology, right? We take the continuous linear functionals and we take the inverse image of open sets, right? That's how we form subbases and then we make some finite intersections and then unions. That's how the whole weak topology is formed. So this is a weakly open set which contains X naught. See, from this thing. X naught is contained in O and O is a whole contained in W complement from this. Okay. So we got an weakly open set containing the point X naught containing a whole W complement. That means this proves that W complement is weakly open. That is W is weakly closed. So what's the gist of this theorem? The norm closed convex subset of a norm linear space X is weakly closed. Okay, this is the theorem. So by that we can straight away take the second option. That means W is closed, which implies W is weakly closed. Okay. Now third option, the weak closure of W and the norm closure of W coincides. So if I take norm closure is closed. Okay, I mean closed. When I say closed, it's okay. No need to explain. I think closed means you just consider closed means non-closed. Okay. When I want to say weakly closed, I will explicitly write weakly closed like this. Okay. Whenever I say we closed, it's non-closed. W closure is closed and convex. This will imply W closure is weakly closed. Okay. So I want to show. Uh, okay. We want to prove here W this thing. Okay. This I write for weak closure. This is not norm closure. This I want to show equals to norm closure. Okay. One side is always true. That one side is always true. Which side? That W closure is contained in a quick closure. How is that true? Like if you take any X belongs to W closure, okay, that means any open set containing X intersects with W. Correct? That's what it means. But the best thing here is if you take only any weakly open set, that is itself norm open. Right? Every weakly open set is norm open. Okay. So this is you can try to prove this. This is very simple. In fact, I'll prove this in some later question. It is required. Every weakly open set in is norm open. That implies if you take any open set, any weakly open set, containing X, I call it suppose V. V is the weakly open set containing X. Then V is open in norm also. That means V intersection W minus singleton X is not equal to phi, right? Oh no, no. Yeah, it's just in closure, right? So it's not needed. Yeah. So that's all, right? That's what we wanted. Like any point in the W closure that's norm closure, it is also in V closure. Yeah. So W closure is contained in W V closure. Okay, that one side is true. We want to prove other side now. Like uh, W. This follows from the previous lemma I said. Like W closure, norm closure is closed. It's weakly closed as well from the previous lemma set containing W. Correct? But if you take weak closure of W is the smallest closed set containing W. That means W closure is contained in norm closure of W. So from 1 and 2, norm closure is same as weak closure. Okay. So from this, the third option is also correct. Okay. Yeah, that was clear, right? If you have any doubt in between, you can ask. Okay, we'll go for the question number 4. Let V is C01. S is the simply two radius ball, not ball, sphere in V. And this is how K is defined. Which of the following statements are true? Uh, so, what do you want? First option says that the S is weakly closed. Okay. S is 'Okay. So weakly closed means what? The weak closure should be in the set only, right? That's the definition of closure for any set. The closure should be in the set only. It is same as the set. But what I'll show is 0. Okay. We'll show that 0 belongs to the weak closure of S, and obviously 0 doesn't belongs to S. So S is not weakly closed. So let U be any open set containing 0. Open means weakly open. 0 means here it's a 0 function, okay, constant 0 function. 0 element of the vector space V. This. So U be any weakly open set containing 0. Okay. So how is the weak topology formed? It is the just collection, like the basis of weak topology is what? The basis collection of intersection of Fi inverse of Ui's, I going from 1 to n. N belongs to natural numbers and Fi's belongs to okay, V star, and Ui's are subset of R which are open. This is how the basis is formed. Correct. Now since U is an weakly open set containing 0, it has a basis element, right? So kind of there exists some I'll say phi i's, 1 less equal I less equal n, such that uh, intersection of phi I inverse of the open set minus epsilon to epsilon I going from 1 to n. Okay, I going from 1 to n. This is contained in U. Okay, this step you just go through once again when you redo it, because this is kind of crucial step. I'm taking this UI as UI as minus epsilon to epsilon for every I. Okay, this can be done. Okay, like for UI can be anything, but I'll just take the intersection of all those UIs, then also this will work. Okay. So let's just go through this step once again. So this is possible. That means what? If X belongs to V, okay, is such that okay, X not X, V is because C is 0, right? It is the collection of all functionals. sorry, functions on 0, 1. So instead of writing x as an element of V, I'll write f as an element of V. Okay. Yeah. So if f belongs to V such that modulus of notational confusion will arise. I'll replace these phi fi's with phi i's. See, consider look, the phi i's are linear functionals on the vector space V, which is C01. Okay. So if I take any, if f belongs to V such that modulus of phi I of f is strictly less than epsilon for 1 less than I less than n. So that means what? This means simply f belongs to this intersection, right? This. Because phi of f is strictly less than epsilon. I mean, this phi of f belongs to minus epsilon to epsilon for all I going from 1 to n. And this implies x belongs to u, right? So if this happens, then x belongs to u, right? That's all we know. Now, consider a function capital phi linear functional from from V to Rn given by phi of f as phi 1 of f, comma phi 2 of f, with this phi n of f. Okay. So this capital phi is a linear function. Okay. Continuous also is a linear continuous function. And what is the dimensions of V? V is infinite dimensional, right? That means null space of phi has to be non-zero. Okay, by simply you can think of this as a rank nullity theorem because the range space is finite. The range is in Rn, so null space has to be non-zero. Otherwise, V will become finite dimensional space. Correct. So null space has to be non-zero. So if an element x belongs to null space of phi, that means what? Sorry, not x. F. Phi of f is 0. That means component wise, each component 0, which means phi I of f is 0, right? Which means what? Modulus of phi I of f is strictly less than epsilon, right? And epsilon is fixed here. So from this condition, what did we can say? F belongs to U, right? Correct? Yeah. F belongs to U. But since phi null space of phi is a subspace, we can always find an f belongs to null space of phi such that norm of f is 2. That means U intersection the S that's defined the function S this set is non-empty. So just recalling what we have done is we have taken an open set U, weakly open set containing 0, and we got an element U intersection S as non-empty. Like this is happening for any weakly open set containing 0. That means 0 belongs to weak closure of S. That means S is not weakly closed. Okay. Any doubts in this? Yeah. Okay. If no doubt, I'll continue. I'll go to second option. The set K is closed. Okay. Okay. So in fact, if I define a new function phi as phi of f equals to integral from 0 to half ft dt minus integral from half to 1 ft dt, then verify that phi is continuous linear functional and K is just phi inverse of singleton 1. Hence, singleton 1 is closed, that implies K is also closed. And we have, and here K is convex also. And from the lemma we have seen just now, every convex and norm closed set is weakly closed. That means set K is weakly closed. Can you see what is on the screen? It seems very small. Yeah, now it must be clear. Okay, so what's the question? Let V be a Banach space and VW denote the space V equipped with the weak topology. Let T from V to V be linear map, which of the following statements are true? If T from V to VW is continuous, then T is a linear. The T uh, is continuous from V to V. Okay.
Sir, fifth question, sir.
Yeah, we have done right. Fifth question just now. Oh. Oh my God. I missed fifth question. Oh, I'm sorry. I made a mistake. I didn't wrote the fifth question. Can you tell me if it's possible? What is the fifth question? Just a minute. I'll write it here. The fifth question. I have the PDF.
Sir, B is Banach.
Yeah. Yeah. I got it. I got it. Yeah. Actually, the same first statement is same. Actually, yeah. Only the options are different. Correct?
Yes, sir.
Yeah. So like right here, what we have to prove is, I mean, check whether first option says that T from V to VW is continuous. Second option says that check whether T from VW to VW is continuous.
W to V, sir.
Second option.
Correct, sir.
Yeah. Third option, T from VW to V is continuous. This is the question number 5 we want to check. So where VW is the vector space V equipped with the weak topology, and T is a operator, linear continuous linear operator from V to V. Okay. There is a result which will be used nicely here. I'll state that. So this result is for any general, you know, a vector space. Like if suppose Oh, okay. X and Y be topological spaces, and Y, okay, and you think of a family of functions, script f to be a family of functions, linear functions or something from Y to R. Actually, this is not just from Y to R, this can be from Y to uh, Zi, where Zi are topological spaces. Gamma. And now from the script f we can define a topology on Y, same by the same logic as we have defined the weak topology. Okay, then any function f from x to y is continuous if and only if fi composed with f from x to zi is continuous for all I belongs to gamma. Okay, like what it says basically, this is x, this is y, and Jedi's are there. Suppose this is one particular Jedi. There are so many Jedi's. Okay, so you have a function f here, and you have the functions fi is here. So this function is continuous from x to y and only if you compose these functions f composite fj, f composite f2 like this. So f composite fi, f composite f2. If these all are continuous, then you can say that f is continuous. It's an if and only if theorem. It's a big theorem actually, just topological in topological spaces. Here, how this theorem is useful is because you have from V to VW, uh, so that map T is from V to VW, T, and from VW to R, you have all the linear functionals, right? F belongs to V star. From this family of functionals, V star, we define the weak topology, right? VW. So, according to the previous lemma, V is continuous if and only if F composite T, this will be from V to R, is continuous, right? For all F belongs to V star. So what we know, F is continuous, T is continuous, they have given, right? Yeah, like I mean, F T, just a minute. T is bounded, right? T is bounded linear continuous operator, and T is continuous, F is continuous, so F composite T is continuous from V to R, right? So this will imply that T from V to VW is continuous. This is a simple use of this theorem. You try to prove this theorem if you have some basic knowledge of topological vector spaces. So this theorem is easy to prove. I mean, not so easy, but if you know some topological properties, then okay. So here we have proved that T from V to VW is continuous. Okay. Yeah, provided in the question what we have is T belongs to L of V. Right? That means it's a linear continuous function. Continuous in the sense non-continuous. Okay. So, so part 2. So part B says T from VW to VW is continuous. So by the same logic, yeah. See, right now we have proved that from V to VW T is continuous, and from VW to VW to W identity is a continuous mapping, right? Hence, the composition, yeah, the composition will be T from, no, no, sorry, we want T from VW to VW. Okay, just a minute. Anyone have any idea about this thing? How to deal with this VW to VW? Okay, this follows from definition itself. Okay, yeah. See, T is even though V has topology, weak topologies, but T is linear, right? T is linear and norm-continuous. Okay, so for every F belongs to X star, F composite T is also linear and norm-continuous. So by definition only, what is weak topology on V? It is least topology such that every linear functionals are continuous, right? Every norm-continuous linear functionals are continuous. So because F composite T is itself a norm-continuous linear functional, so F composite T is continuous for all F belongs to X star. So by the previous lemma, this follows that F is also T is also continuous from VW to VW. Okay, this follows from this lemma. Okay, this one. Here. Okay, so yeah, the C option of VW to V. Yeah, this need not be true because with V we have the norm topology. Okay, which is kind of larger than the weak topology. So, for example, if you take T to be identity function, identity mapping, suppose, then the identity mapping is continuous, norm continuous, but not weakly continuous, not like that means there are some norm continuous open sets whose inverse image is not weakly continuous. Oh, sorry, norm open sets whose inverse image is not weakly open. C is not true. The question number 6 is a problem now. Hmm. Okay, so I'll just write that question number 6 here. Which says T is just a linear map. V Banach space. First option says T is from V to W continuous, then T is linear continuous. We'll check this. Okay, so T from V to VW is continuous. That means this here it's norm topology. This here is weak topology. We want to show is continuous. Where these two both sets are considered now as in norm topology. Okay, Just a minute. Hmm. Okay. So we can show this by sequential criterion. So like suppose you take xn is a sequence in V such that xn converges to x, and since t from V to V to VW is continuous, which implies txn converges to tx weakly. This is the symbol for weak conversion. Uh, no, this. No, just a minute. Okay, we'll come to this question number 6 later. I will go ahead. Uh, I think I have doubts. I have some doubts in this question number 6. I'll explain this maybe later. We'll go to the next question. Sorry for that, question number 6. So question number 7. Let En denote the sequence which has 1 in nth coordinate and 0 elsewhere. Which of the following statements are true? I'll explain that question number 6 in the this also. This PDF I'll update and then upload in the Excel sheet what you will get. Okay. So don't worry, the answer will be given to you. En denote the nth sequence which has a 1 in the nth coordinate and 0 elsewhere. Okay. So first thing it says En converges to 0 in C naught. Okay. So this happens if and only if like f of En should go to E0 for all f belongs to C naught star, right? This is one condition for weak topology, right? But if you take f as uh, okay, yeah, yeah, this should happen, yeah, yeah. And what is C naught star? C naught star is L1, you know, right? So like f of xn should be equal to summation xn yn. Okay, so okay, not like this. That means for every f belongs to C naught star, there exists some y belongs to L1 such that f at x, like f at xn equals to summation xn yn, and going from 1 to infinity. Right, this should happen where y is yn. This belongs to L1. Okay, this should happen. So what is f at en? Other than the nth term, all other entries are 0, and on nth term we have 1. So f of en will give us yn, right? So since y belongs to L1, right? So summable sequences. You know, if a series converges if and only if it's its nth term, not if and only if series converges, then its nth term goes to 0. Hence, then this yn should go to 0. And this is happening for all f. Right? This implies en converges weakly to 0. Okay, so the first statement is true. The second statement, okay, second, the same logic, if we take f of like xn equals to summation xn infinity, then f is a linear functional and f at en is what 1, and fen doesn't converge to 0, right? This implies en cannot weakly converge to 0. Okay. The last part, yeah, with the same logic, p from 1 to infinity. Okay, no, just a minute. Yeah, with the same logic as of 1. Okay, so like see, LP star is LQ, right? For all p from 1 to infinity. So if we take any f belongs to LP star, there exists some y belongs to LQ such that f of xn is equals to summation xn yn and going from 1 to infinity. So implies what will be f of en? F of en will be equals to yn, right? But since yn belongs to LQ, this goes to 0, right? This implies en converges weakly to 0 in LP for all p1 to infinity. So seventh is settled. Question number 8. So xn is defined like this: 1 half, 1/3, 1 by n, and then after all 0. The sequence xn is weakly convergent in L1. Okay. Okay. So if we define the function f from same like L1 to R given as f of xn equal to summation xn, right? Then f is a linear functional, but what is f of the sequence xn? This diverges, right? That means this cannot converge weakly to any element. Then the sequence xn is weakly convergent in LP. Here, see, in nonlinear spaces, sequence converges in norm, then xn converges to x weakly. Weakly. That we know. Here, in every LP spaces, this xn converges to the element x, 1, simply the 1 by n sequence, not 0. In norm. This implies the sequence xn is weakly convergent in LP. Yeah, also in L infinity also it converges to the same x, okay, in norm. So also it converges weakly there also in L infinity. So question number 9. V be Banach space, Xn be sequence in V, which of the following statements are true? Okay. Xn converges to X weakly, then there exists a subsequent Xnk such that norm Xnk converges equals to norm X, I mean limit. Okay. So this is wrong. You take H be a Hilbert space and say Un, suppose, or En be an orthonormal set. Okay. Then like claim is En converges to 0 weakly. So how does that follow? For on a Hilbert space, for all f belongs to H by Rees representation theorem, there exists some y belongs to H such that f of an element x equals to inner product of x with y, right? But for orthonormal basis, if sorry, not orthonormal basis, for any orthonormal basis, this sequence, if you consider, this converges to 0, right? This is happening for all x. This follows from the Bessel's inequality. Not Bessel's, I think Parseval's. Yeah. Or some inequality, Bessel's or Parseval's. Hence, what will be the f of En for every linear functional? This is inner product of En with y. And this goes to 0, which is f0. Hence, En converges weakly to 0, but norm of En is 1 for all n belongs to natural numbers. But norm 0 is 0. Hence, there cannot exist any subsequence nk for which norm enk converges to norm 0 because it will be 1 always. So this is not possible. Second, if xn goes to x weakly and this happens, then norm xn goes to norm x. Okay. Okay. So by Hahn-Banach, we know there exists f belongs to x star such that f of x equals to norm x, right? And norm f is 1. This is one consequence of Hahn-Banach theorem. So as xn goes to x weakly, where does fxn go? Fxn goes to fx, which is norm x. So this is a real number sequence which is converging to norm x, which implies there exists n belongs to natural number such that fxn is strictly greater than norm x minus epsilon. Like for any epsilon positive, this is happening. Correct? Like what that means is if you take a ball centered at norm x epsilon ball, then after some point fxn belongs in this ball, right? That's what this means. Okay. And what we have is f of xn will be less equal modulus of fxn, so less equal norm f into norm xn. Norm f is 1 and norm xn is less equal norm x. That means fxn are always less equal norm x plus epsilon, right? Okay. Or we don't need this. Yeah. Yeah, this only we need, that norm of xn is greater or equal fxn, which is strictly greater than norm x minus epsilon after some n. And what is given is norm xn is less equal norm x, which is strictly less than norm x plus epsilon, right? This implies this norm xn belongs to, so this will prove that norm xn converges to norm x. So second is true. Third part. Third part says that if xn goes to x weakly, we also have norm xn goes to norm x. Okay, then xn goes to this. Okay, this seems wrong. Okay, you take xn to be e1 minus en. It belongs to c naught. So what are these xn's? Are this like x1 will be 0. 0 means 0 sequence. X2 will be 1 minus 1 0 0 0. X3 will be 1 0 minus 1 0 0 0. Like this. These are xn's. So where does xn go? Like, for every f belongs to c naught star, which is L1, f of xn equals to, mm, I guess, y1 minus yn, right? Where will this go? This will go to y1, which is f at e1, which implies xn goes to e1 weakly. Okay, xn goes to e1 weakly. What else we have? Yeah, also norm of xn is same as norm of e1, which is 1. So xn also goes to e1 weakly, and norms also goes to e1. But what is norm of xn minus e1? Which is norm of en, which is 1, which doesn't go to 0. Okay, so this third one is wrong. So question number 10th, let L2 be identified with its own dual. Okay. So when you identify L2 with its own dual, A star is simply adjoint of A. Okay, so the operator A is given is this. We want to find what is adjoint of A. Okay. So you know what is the inner product of L2? Inner product of x with y, okay, is summation xi yi bar. I going from 1 to n. Okay. So what is inner product of ax with y? Summation xi upon I yi bar from 1 to n is equal to summation xi into yi by I bar, I going from 1 to n. Sorry, not n. Sorry, infinity. Which is equals to inner product of x with ay. So this will prove that A equals to A star. Okay, so first option is true. The next is, let n be a fixed positive integer, then ax is this, then A equals to A star. Yeah, same as this one. There is no different thing. Only instead of infinity here, it will be replaced by n. All other things are same. So I just leave it to you. Part B. And the third one is a right shift operator. So what will be the inner product of ax with y equals to summation xi yi plus 1, I going from 1 to 1 to infinity. So this can be written as inner product of x with a star at y, whereas a star at y is given as y2, because see, it will start from y2, okay, y2, y3 and all. So it's a different operator. The a is the right shift operator, but what we are getting as an adjoint is a left shift operator. So a is not the same as a star. Yeah. Okay, any doubt in that? The question number 6 part I'll give you posted on the Excel sheet. So don't worry, I'll explain the next class, next session also. So yeah, today's session is over. If you have any doubts, you can ask.